All right. Hello and welcome to the 2024 QCE Chemistry July lectures at ATAR Notes. First of all, my name is Noor. I graduated year 12 last year and I'll be presenting the lecture for you today. But just before I get started on content, I just want to talk to you guys a bit about ATAR Notes and who we are and what we have to offer. Okay. So, first of all, ATAR Notes, what we are is we're an Australia-wide website, and our main focus is to help high school students, particularly in year 11 and 12, achieve their ATAR goals. So then how we do that is we do have TuteSmart, a service for private tutoring. We have classes. We also have a lot of high school resources that we offer, which are there to help to help high school students achieve their ATAR goals. So a little bit about some resources we offer, some free services we offer. We have a lot of study notes, hundreds of study notes, all for free, available on our website. So make sure to check that out. If you're here, then you probably already know about the lectures. So those are also free services that will help you a lot consolidate content and things like that. Um, we also have a discussion board, so you can see other questions people might have about ATAR, about the QCE, about content. You can also ask your own questions, see what other people have to say, see what we have to say as well. We also have some revision videos for people studying for their ATAR, and these I'm sure will help a lot with the content. Um, Another thing we have are some newsletters, so that way you know about like any curriculum changes, any like anything that happens in terms of the QCE and ATAR. Those are an excellent resource for that. We also have the ATAR calculator, which I'm sure a lot of you probably know about, a lot of you have used. I personally have used it a lot in year 12. It's a really good tool to help you see if you're on track or not. For me, like a lot of the time helped me not be stressed. Sometimes it made me more stressed, but that's all for the best because sometimes even if you're not on track, it's a good reminder so that way you can be more motivated. We also have some articles on study strategies and exams, like exam strategy and things like that. Because in my opinion, like I think knowing the content is obviously very important. But so is exam strategy, and that doesn't seem to be the focus for a lot of people and a lot of teachers as well. So exam strategy is also very important, and these articles will also help you develop that as well. Now, with all these resources, they are all free, so make sure to go to our website and check that out. But we also have some more comprehensive resources if you purchase ATAR Notes Plus, and those are just like they are awesome. They are amazing. Um, so we have like our, for example, AI tutors. If there was something you didn't understand, something you quickly wanted to check, we have like AI to help you with the content. We also have, flashcards, for a lot of, QCE subjects, things like that. We also have, course revision notes for, a lot of the year 11 and year 12 subjects. We have topic tests for you to practice, prac exams, I'm pretty sure. So there's a lot. So I also would highly recommend ATAR Notes Plus. But that is all about us and who we are and some of the resources and services we have to offer. Now let's get started on the lecture. So, for me, I think the main focus on this lecture will be Unit 4 content. The only reason why I think why I've haven't included things like organic functional groups, organic pathways, things like that is because I think they were already covered in the April lectures. Um, And yeah, so today we're gonna start with macromolecules, um, which cover part of topic one and also part of topic two, and the analytical techniques, which are mainly part of topic one. And then we're going to talk about some chemical synthesis and some stuff from topic two. So the Haber process, the contact process, biodiesel and ethanol production. And we'll also talk a little bit about um, some green chemistry and some parameters we use to assess, how green a reaction is. And don't worry just now, like this will all make sense when we cover it. All right. Now, here are some syllabus dot points and cognitive verbs. I haven't included them for every single topic we'll do because there's just not enough slide space for that. But I highly would recommend that when you're studying for your exam that you are constantly using the syllabus to check if you know what you need to know for the exam, because this is what people who write the external exams actually use to um, like write your exam questions. So I think it's always really important to look at those and think about how they can be used to make an exam question, and also where you are in track of knowing and understanding these dot points. All right. So let's get started on macromolecules. So before I jump into all the details with all the content, I just want to talk a little bit about just an overview of what macromolecules are and where they come from. So just in terms of just scientifically, we know that, the word micro usually refers to something really small that we can't see. Macro is something that's, on a bigger scale. Um, so obviously with molecules, there aren't really molecules that are big enough for us to see, like a single molecule, but macromolecules usually just refer to really big molecules. So if you've like one example, and I'm sure the people here who are passionate about gym and fitness have probably already heard this word before. Hitting your macros. Yeah, so that's where it comes from, because these macronutrients, like lipids slash fats, like carbohydrates, like proteins, they're all examples of macromolecules. Um, so that's basically like where the word comes from, and these are the applications of it. And that's mainly what we'll talk about in this section. We're going to talk, our main focus will be carbohydrates and their structure, lipids and their structure, as well as proteins and their structure. All right. So when we talk about carbohydrates, a lot of the time I really like to think about the empirical formula, because it basically explains where the name comes from. So the empirical formula for any carbohydrate is CH2O. So C, carbo, H2O, hydrate. So that's where the name comes from, basically. Um, and when we talk about carbohydrates, we talk about, when we say sugars, we're talking about things like glucose, an example we might be familiar with, and their dimers and polymers. Now, if you're unfamiliar with the word dimers or polymers, I'll just explain quickly what they are right now in case you haven't covered it. So, when we talk about a polymer, we're talking about like a big sequence of molecules that are covalently bonded, um, not with intermolecular forces. So they have to be covalently bonded, and it has to be individual molecules that are either the same or really similar. Um, and they're bonded roughly in the same way, or roughly in the same place across the whole polymer. So when we think about carbohydrates, when we talk about polymers, we are talking about, see this molecule here. Imagine if we had a sequence of 200 of them, all covalently bonded. That's what we'd consider a polymer in terms of carbohydrates. So, and we take the whole polymerization aspect into account when we classify the carbohydrates into different types. So the first type is the monosaccharides, and these are carbohydrates that haven't undergone polymerization. So things like the molecule we can see in front of us, that's an example of a monosaccharide. When we talk about a disaccharide, then we have two monomers. Sorry. So basically, with the disaccharide, it's basically when we have like, say if we had two of these molecules that were covalently bonded, that would be an example of a disaccharide. If we had three or more, that would be an example of a polysaccharide. Sorry. Okay. So let's talk about each of the individual types and some of their properties. Okay. So monosaccharides, as we just mentioned, are individual units or individual monomers. Um, Main property we have to know about monosaccharides is that they're polar and soluble. Why are they polar? Let's look at their atomic structure. Um, so as you can see, basically every carbon in the ring is bonded to an OH group. And as we know with OH groups, they form hydrogen bonding because of the difference of electronegativity between the oxygen and the hydrogen. And the way these OH groups are placed doesn't cancel the polarity, just going back to some year 11 concepts. So because of that, we have all monosaccharides being polar. Of course, each of them are polar to a different degree, and we'll cover that in just a little bit. Um, but all of them are polar, and therefore they're soluble because water is polar. So, there are like individual monosaccharides that you have to remember and know the properties of, and I've got those listed or drawn out just at the bottom of the slide. So, if you can see the picture at the bottom left and the bottom right, those are both straight from your data book. So those are not molecules I'd be too stressed about remembering because they're already there in your data book. But it's still really important to know their properties and to know the differences of their structure and how that affects their properties. So first molecule we have at the bottom left is alpha glucose. So glucose comes in two isomers, the alpha glucose and beta glucose, or two isomers that we need to know in year 12. Main difference is that if we look at carbon 1, we can see that in alpha glucose, we have H on top, OH on the bottom. In beta glucose, we have OH on top, H on the bottom. What that means then is that alpha glucose is actually more polar than beta glucose. And why is that? That's because we basically, if we look at the OHs, remember for our polarity not to cancel, um, we don't want to like have, and I might just exit and just like annotate a little bit. So, if you look here, right? So we have like, this is sort of pulling down, this is sort of pulling down, this is pulling down, and then this is pulling up, this here is pulling up, right? Just in terms of electrons and polarity wise. Whereas when we look at beta glucose, we have up, down, up, down, up. Here we have three ups, two downs. Here we have three ups. Sorry, here we have one, two. Yeah, so here we have, yeah, three ups, two downs. Here we have three downs and two ups. So then what that then overall means is that we have more of a difference in the alpha glucose, which means it's going to be more polar. But that's the main thing, properties that we need to know about in terms of monosaccharides. All right. So that's all there is to monosaccharides. Let's jump onto disaccharides. So disaccharides, they are basically two monosaccharides that are covalently bonded. And I'm just gonna put an empty slide just so I can explain a little bit how that bonding happens. Um, so let's look here. All right. So let's draw out two glucose molecules. Actually, I might just copy this picture from the slide and have two of it here. Oops, sorry. Sorry about that. All right. See, here we have two glucose molecules. Um, and this is how they form polymers. This is the bond. See how here we have carbon 1, right? Let's number these carbons. So 1, 2, 3, 4, 5, and 6. We have 1, 2, 3, 4, 5, 6. Let's look at carbon 1 and carbon 4. We have two OH groups. For them to covalently bond, what happens is that we basically, one of the H's here will go, the OH will go here, we get H2O, and then that O will bond to that carbon 4. And that's what we call a condensation reaction, because we're getting rid of, or we have water as a product. So let's write condensation reaction. So this is how we get, this is the type of covalent bond they form to make monomers or polymers. All right. So molecules, and let's just go here. Glucose condensation reaction. And also, another point to actually keep in mind here is that this covalent bond that the oxygen from this glucose forms with the carbon 4 of the other glucose, that's what we call a glycosidic bond. It's this very specific type of bond that actually forms when glucose or alpha glucose is forming polymers or diamonds. All right, now we know how they polymerize. Let's actually look at some examples of disaccharides they make and talk a little bit about their properties as well. So with disaccharides, as we said before, they are two monosaccharide units, and there's three types that we actually need to remember. But before we actually talk about the individual types, let's talk a little bit about their polarity. So we look at disaccharides. We have this same, we still have these OH groups. And then when we have these OH groups, what happens is that we're still having that uneven distribution of charges and therefore the polarity. So disaccharides are still polar. The examples that we need to remember of disaccharides are lactose, which is, and let me, I don't know if I can write when it's presenting, is this one here. This is lactose. And lactose is a glycosidic bond between glucose and galactose. Now, you don't need to actually know the structure of galactose. It's basically just an isomer of glucose. In terms of the syllabus, you don't need to know it. It's not listed under the monosaccharides. You just need to know that it is part of the bond that is formed with glucose, which forms the lactose. Like, you need to know that lactose is glucose and galactose. You don't need to know a lot about galactose. We look at the second type, which is maltose, and that's this here. And what maltose is two glucose units. So we can see it's basically the bond that I just described in the last slide. So we can see how we had like one OH and one H from each of those carbons leave to make a water, leaving that one O to form this glycosidic bond. Last type is sucrose. And sucrose is a bond between a glucose and a fructose. And this also happens at carbon 1 and carbon 4. One thing we also need to just keep in mind with those is just like examples in real life. So we know that lactose is found in milk. That's probably where, like, if you heard the term lactose intolerant, that's where it comes from. It's people who don't have the digestive enzymes to digest the lactose in milk. We have sucrose. Sucrose is basically just like table sugar. So it's the sugar you put in your tea. That's actually sucrose. And then we also have maltose. All right. That's all there is about um that's all there is about like disaccharides. Now let's look at polysaccharides. So they're polymers of monosaccharide units and also undergo condensation. But there's many different types because they all bond in different ways. So we look at, say, for example, amylopectin. Um, it is bonded as alpha 1 4, but it kind of forms branches. Like it's sort of, if we try and draw it out, right? Or I might draw it, just do the drawing next to it. Like this is a glucose, right? Oops, sorry. So if we have this is a glucose here, right? This is a glucose here, and it forms like this sort of chain. But then we also have sort of branches like that. And that's why it's alpha 1 4, alpha 1 6. So the 1 6 is basically what forms these branches. Um, so basically, then once we have these branches, then that makes it, or we won't talk about polarity yet. Let's just try and actually visualize them first. If we look at amylose though, same as here, whereas it's just a straight chain of alpha glucose. Um, and that's the same with cellulose, except it's with beta glucose. And okay, so this is alpha, both of them are alpha glucose, and that's beta glucose. And that's where when we talk about alpha 1 4 bonds. So alpha for alpha glucose, 1 4 for carbon 1 of one glucose molecule bonded to a carbon 4 of another glucose molecule. That's where these names are coming from. Now, when we talk about polarity, these aren't going to be like the monosaccharides or disaccharides because there's so many of them that they'll eventually they'll sort of form circles. The OHs will sort of start forming hydrogen bonds with each other, so they can't actually form these hydrogen bonds with the water. um so because of that they end up being non-polar. um or if we talk about polysaccharides, basically all of them are non-polar. Some of them are just slightly more soluble than the others. So when we talk about amylopectin, it is still branched, so there's still going to be some glucose molecules that are where the like OHs are still available for these interactions, so it's slightly more soluble than the others. um then we have amylose. Whereas amylose, it's a straight chain, so eventually they are going to start forming hydrogen bonds with each other and things like that, um, and eventually, like, will not be polar and will not dissolve in water. Cellulose is even more rigid because we have beta glucose, which is already less soluble than alpha glucose. So that's basically where this order comes from. Um, all right, so that's basically all there is about carbohydrates. And just remember, this is a recording, but I'll be there in the lecture to answer any questions you may have. So if anything is not making sense so far, please make sure to type it in the chat. All right, now let's talk about the next category of macromolecules, which are lipids. All right. So lipids, there are many types of them. For example, fatty acids, steroids, phospholipids. But the ones we actually need to know um, in year 12 mainly are like things like fatty acid salts, and like other than fatty acids, it's just sometimes, like esters, because esters can be lipids. And we'll talk about how that works in 1 second. Um, But the main thing to remember about lipids is that they're all non-polar. And therefore none of them can dissolve in water. And also they're going to have lower melting and boiling points than water. So if we think about it, why are they non-polar? It's because essentially what they are is they're carboxylic acid chains, and then you might think, well, carboxylic acid, we have an OH bond, we have a C double bond O. Why is it non-polar? Well, it's a really long carboxylic acid chain, and we only have the one carboxyl group. And then what that means is that the polarity that this carboxyl group forms just starts canceling out the longer that hydrocarbon chain or hydrocarbon backbone is. Um, and that's why when we talk about fatty acids, for example, they're non-polar. Same with like polyesters. We already know polyesters are even less polar than carboxylic acids. And then when we have a really long chain on this side, really long chain on this side, essentially that little oxygen bond in the middle isn't going to do much. And the effect of its polarity becomes less. So when we classify lipids, and this is where we talk mainly if we think about the fatty acid example. If we talk about a saturated lipid, we talk about a lipid where we have only single bonds. And this works in the same way as like when we talk about hydrocarbons. So remember, if it's only if it's single bonds, and there's going to be more hydrogen atoms bonded, therefore more molecules, and a higher molecular weight. What then that means when we think about London dispersion forces is that like our temporary dipole is going to be stronger because our molecular weight is more, and therefore our melting and boiling points will be higher. So for example, an example of saturated lipids are animal fats. And that's why you notice animal fats, an example of that is butter. It's solid at room temperature. And that's because it's a saturated lipid. When we talk about unsaturated, we have a lot of double bonds. And when we have double bonds, that's less less atoms in the molecule. And once again, with London dispersion forces, when we have a lower molecular weight, then we have basically we have like a higher melting and boiling point. And that's why when we think of plant fats like vegetable oil or canola oil, things like that, they're all liquid at room temperature. All right. So one application of lipid we have to be familiar with is soap and what we call saponification, which is the reaction we use to produce soap. Now, how we produce soap is we get like our reactants are triglyceride, and which is a type of lipid, and sodium hydroxide. So how this works is let's look at the lipid in the reaction here. All right. So and so if we look at the lipid here, right, we can see as I talked about properties, see how we have like this ester group here. And this is an example of a polyester. Well, not necessarily a polyester, but this is an example of like a lipid that's made from an ester, not necessarily a carboxylic acid. Um, you look here, see how we have this ester group, but then we have like a 15 carbons here. So very long chain. That ester group doesn't have much of an effect anymore. And that's why it's non-polar. All right. So with this reaction, and I'm gonna talk about in a minute how it's actually how our product is useful as soap. Um, but first of all, let's talk about this reaction and how it works. So we have our triglyceride here, and we have 3 sodium hydroxide ions. What then will happen is that see those OHs? They're gonna go here. They're gonna bond to here, right? And then these oxygens will ionize. And then that's how we get this part right here. And then our oxygens ionize, right? So they're all negative. remember the Na atom is positive, so then it bonds to whatever's left here. Um, and then now we have this molecule, but we have three of it here in this reaction. So let's keep that in mind. And this molecule is what we use as soap, or the main ingredient in soap. So, why is this molecule, if we think about properties, why is it useful as soap? It's because when we draw it, and I'm just going to cross this out and write positive because that's what it should be. So, when we draw the molecule out, it looks something like this. We have this little sodium. We all know that sodium ions are soluble. And then we have a really insoluble. Sorry. We have a really insoluble backbone here. We have a really insoluble tail here. All right. So then, what happens, right, is that we know that nonpolar or insoluble attracts insoluble. So we can see here how in this molecule we have these tails all attaching to the grease, right? But if we look at the head is still soluble. So eventually, after enough molecules have attached, they'll sort of break the grease on your hands into little balls like that. And then this head will dissolve in water and will be attracted to water. So then when you wash the soap away, the grease will go. So that's basically why this is useful as like that's why this molecule is useful as soap. Because imagine if you had grease, right, on your hand. Like say you ate fries, the oil is still on your hands. You want to wash your hands. Well, oil's insoluble. The water's not going to take it anyway. You put soap, that's going to wash it because of this mechanism of action. These non-polar tails will bond to the oil, break it into these little balls, and this is all on a molecular level. And then eventually the polar head is still soluble in water, still attracted to water. So you wash it off, grease is out of the way. All right, that's all there is to talk about lipids. Now let's talk about proteins a little bit. So, before we actually think about what a protein is, we have to because we have to talk about what an amino acid is, because amino acids basically are the monomers of proteins. So we think about an amino acid. We have this is the structure for any amino acid. So we have a chiral carbon, we have a central carbon. On one side, it's bonded to the carboxyl group here. On another side, it's bonded to the NH group here. And then that leaves two electrons to bond. So then it bonds on a hydrogen and then a side chain. And the side chain is what makes, the 20 different amino acids different from each other and makes their properties different. All right. Now, we can't really talk much about proteins before we actually understand how amino acids work. So when we talk about amino acids in solution, this is what makes them unique, is that they're also amphoteric. They're like water. They act as an acid or a base. And then we think about that. How does that work? It's because, see here, I'm going to go back to just the original structure. What can happen is that, see, this is a carboxylic acid group. We know this group is acidic. So this H plus can be donated. And then we end up with a COO negative. And this is an amino group. This can actually accept the proton, right? And then we end up with an NH3. Write the 3 on the right side. Plus. So this means that the amino acid can actually both donate and accept a proton. And this is why where the name zwitterion comes from. It's because we have two charged functional groups here, but the net charge becomes neutral. So that's basically where the name zwitterion comes from. But the main thing we need to talk about with amino acids is that it's not always a zwitterion. It's only a zwitterion under neutral conditions. So if our conditions are not acidic and not basic, then the amino acid can have a neutral charge. Um, so under acidic conditions, if we think about it, there's a lot of there's a lot of protons in solution. So a lot of these protons in solution will bond to this NH2 here and make it positively charged. And then this here will try to donate, but these are not gonna bond to the NH2 in the molecule because we already have a proton from the solution that's bonded to it. So it's just gonna come back and bond back to the carboxylic acid. So we end up with a cation. With basic conditions, it's the other way around. Um, so we basically have a solution that is very basic. It accepts protons. So then this carboxylic acid group is donating protons, but the solution is taking them before the NH2 can. So the NH2 is not ionized, but the carboxylic acid group is. And that's how we get an anion. All right. So now we understand how they behave, but let's talk about something we call the isoelectric point. Um, and what the isoelectric point is, it's because each amino acid is different. Like neutral conditions for amino acids aren't necessarily a pH of 7. Each amino acid has a particular pH that's considered a neutral condition for it. And the neutral condition, or the pH that is considered a neutral condition for each particular amino acid, is called its isoelectric point. So when we come to define it, it's technically the point when the net charge is 0. Now, to really understand this concept, what I would recommend you do right now is jump to your data booklet, look at the list of amino acids. You will see that there is a pH written next to each of them, and that's the pH that's considered the isoelectric point. Now, for each amino acid, if we have a pH that's greater than the isoelectric point, then it's considered in basic conditions and it'll be an anion. If the pH is lower than the isoelectric point, then the pH is, or then the solution is considered acidic, and the amino acid will be a cation. Okay, so we know now about the structure of amino acids. Let's talk about how they bond through condensation. And I'm just gonna just cross this out here and make this into a 2. Okay, so what happens, let me write a 2 here, right? So what happens with amino acids is that here we have 2 different amino acids. We have an OH group from the carboxylic acid, right? And then the NH2, it basically donates or one hydrogen atom. It'll leave the bond and then bond with this OH, and then we get a water. And that's why these are also considered condensation polymers, because the covalent bonds that happen with the polymers are through condensation. So, how this condensation works is that we have one of the H's leaves the NH2, the OH leaves the carboxylic acid group, we have a H2O. And now, this NH by itself will then bond to the C group, to the COO group. So here, then that's what we get as the structure as a result. So we have the NH2 here, then we have C, double bond O, bond to NH, and then bonded to another C. And then that's basically how proteins polymerize. But proteins form many different structures when they polymerize because there's 20 different amino acids. These all with different side chains and different atoms in these side chains, and they all have different properties. So because of this, um, what we get these different structures. The type of structure that we're talking about here is called the primary structure. It's when all these bonds just form a straight chain like this, like straight chain like that, all with individual amino acids just bonded um, through condensation. And this is what we call a peptide bond. And let me write that down here. Peptide bond. All right. So basically, that's essentially what a primary structure is. It's a straight chain of amino acids. But amino acids, because of how different they are, the bonding isn't always as simple as that. So let's look at secondary structure, which is another example of like a type of shape that proteins can take because of the polymerization of amino acids and how these amino acid units interact with each other. So secondary structure is when we have hydrogen bonds between. See here how we have the C double bond O. If we have this is like an amino acid, right? C double bond O, um, and then H, right? And then here NH and side chain. So then this can bond to some other um, amino acid here, right? Um, and then let's go side chain, double bond O and R. So this NH here, the H is slightly positive because remember NH, nitrogen forms hydrogen bonds. This oxygen is slightly negative. We have a hydrogen bond. When that happens across different molecules, we can get two different types of shapes. Here, we have two different chains, right? That are sort of facing each other. They, it's not always two different chains. There'll be like another chain here, and so on. And they'll form like a sheet. That's what we call a beta pleated sheet. And as we can see in the beta pleated sheet, how all these chains are linked together is by this bond between the hydrogen bond between the NH group and the C double bond O group. And that's what we call the beta pleated sheet. All right. Another shape it can do is an alpha helix. So an alpha helix, we actually still just have the one chain. But see how it's sort of, this chain is spiraling. And the reason why it takes this spiral shape is because we have this NH group from underneath, the C double bond O group from the top, and they form the hydrogen bond with each other. And I'm just going to circle some examples of that. So once we have these hydrogen bonds in there, that's essentially what forms the secondary structure, which includes an alpha helix, and that's this first shape here, alpha helix, and the beta pleated sheet, which is where these hydrogen bonds happen across different chains. All right. With tertiary structure, it's bonds between the side chains. So if we go back to the amino acids, see these R groups? These R groups have a lot of different atoms in them. So the interactions between those atoms are what we call the tertiary structure, because these atoms can still form certain bonds, except they don't have to be hydrogen bonds. They can be, but they don't have to be. Let's look at an example of each type of interaction that can happen. Here we can see hydrocarbon groups from two different amino acids. They form a hydrophobic interaction because they're both nonpolar, and they're both attracted to each other. Here we have an NH3, two ions, and they form an ionic bond and form what we call a salt bridge. Here we have an interaction with a polar functional group and water. And here we have a metal ion coordination where we have one metal ion actually coordinates to anions into a certain shape. Here we can still have hydrogen bonds. We can still have hydrophilic interactions. We can also have what we call a disulfide bond, which is the only covalent bond which can occur in a peptide chain. So two sulfide molecules from two different side chains sometimes form a covalent bond, and that's what we call a disulfide bond. And as we can see in this, we still have some alpha helices formed, some beta pleated sheets, as well as all these other interactions. Now, out of all those ones, the main type of interaction I want you to remember is the disulfide bond. And the main thing I want you to take away, you don't have to remember how each single bond actually happens, but what you do have to remember is that the tertiary structure is formed by bonds of all sorts across side chains. Um, so yeah, and when we talk about proteins, that's another thing I want to add. We always talk about how proteins are the most versatile type of molecule there is. The reason we say that is because of this whole structure thing. So the primary, tertiary, secondary structures. And all these different shapes that proteins can form just depending on the individual amino acid units. Because all these different shapes give them a lot of different functions. Whether which can like work differently, whether that's biologically or non-biologically. All right, that's basically all for macromolecules. I just thought that I don't want us to just um overlook it too quickly. So let's basically we've got a quiz here. So let's do it together. And with this one, I recommend that you have your data book in front of you. So because some questions will need it. All right. First of all, which bonds and monosaccharides units are present in maltose? I'm just gonna exit this so that way we can go back to previous slides to actually answer those questions. And I'm just gonna have my Google there so that way we can go to the data booklet when we need it. All right. So which bonds and monosaccharide units are present in maltose? And in the meantime, also, I know this is a recording, but you can still type your answers in the chat if you wanted to. Let's go back here. So maltose, see how we have two glucose molecules and we have carbon 1 here, carbon 4 here. So then when we answer this, let's just write alpha 1, 4 bonds between, and I might just press enter here just to give myself a bit more space. Between two glucose molecules. All right. Which isomer of glucose is the most polar? Let's go back to our monosaccharide slide. So remember, it isn't explicitly stated here, but remember how we did this whole down and up contrast, and we eventually figured out that alpha glucose is more polar. Yeah. All right. Okay. So let's write that down then. So let's go. Alpha glucose. Now, which bonds are present in cellulose? Let's go back to our polysaccharides slide, which is here. So cellulose is a straight chain of beta 1,4 glycosidic bonds. So let's write that down. Straight chain of beta 1,4 bonds. All right. Now explain the mechanism of action of soap. I won't type it again, but I'm just gonna talk through it again. So remember soap? How we have polar head here, non-polar tail. This is grease here. Eventually we get like the polar heads like that surrounding the grease. Um, sorry, the non sorry, sorry about that. Let me redraw that, sorry. So we have, yeah, polar head, non-polar tail. Eventually, this is grease. We have all the non-polar tails attracting it and forming it into just breaking it down into little structures. These polar head then dissolve in water. All right. Here's the question where we need our data book. So what is the net charge of alanine um, in an aqueous solution of pH 7. So what we need to do is we need to look at our data booklet, and I'm just going to scroll through here. So these are the amino acid. Let's find alanine. So pH of isoelectric point is 6.1. pH 7 is more than 6.1, so we have net charge of -1. All right. What is the main bond which forms alpha helices? Um, That's a hydrogen bond between NH group and C double bond O. So let's just draw the bond down. And two examples of types of bonds present in tertiary structure. So we have covalent, disulfide, and hydrophilic, just as two random examples here. And hydrophilic. And remember, there's many other types. There's hydrophobic, there's ionic, um, a lot of different types of bonds. All right. So that's all the answers to the questions on the quiz. I know it's a recording. There's not much time for you guys to try it on your own. I get that, but I hope this sort of helps you consolidate your knowledge, because that'll be all we've got for macromolecules. All right. So now let's get onto um, another big topic, which is analytical techniques. Now, with those, some of those analytical techniques, you just have to understand how they work. Some of them you have to look at data and answer questions. And for the ones where you have to look at data and answer questions, I've got one example for us to practice together. Um, okay, so first one is thin layer chromatography. Um, I think you guys will probably be familiar with this because we did cover it in year 11 slightly. So with thin layer chromatography, we have our stationary and mobile phases. So we're in a piece of paper, right? We have at the bottom, like, let's just say, for example, this is polar here. This is non-polar. We put our mixture in, we put our molecules in. The further the molecule travels this way, the more attracted it is to the non-polar and the less attracted it is to the polar. So then this actually helps us separate molecules um, by comparing their polarities and also, like separate them and distinguish and compare their properties. And this is a retardation factor. So it's basically the distance like it's this distance here over our total distance of the solvent. So that's essentially like a ratio that helps us calculate how much distance there is, and that way we can actually categorize how polar these molecules are. Now, this was mentioned in your syllabus, so it could still show up in the exam. But from my experience with QCEE, it hasn't been too much of a main focus so far. But that being said, anything in your syllabus is something you need to know. So I wouldn't risk not studying it. All right. Now, another example is column chromatography. Now with column chromatography, it works the same as thin layer chromatography. It's just the experimental setup is a bit different. Um, so basically, we have our mobile phase and our stationary phase. Um, so then those two will have different polarities, right? One will be polar, one will be non-polar. And so then when we have our sample, it'll start to like the non-polar will sort of be attracted to the non-polar phase, and the polar will be attracted to the polar phase. And, and then essentially we'll start being able to separate molecules. Because each molecule is unique in how polar it is. Um, and how polar it is will determine how fast it travels through the flask, through the column. So then that means that we can sort of separate all the different molecules in our sample. Now, here's the most important one, and one that shows up in exam questions a lot. And those of you who've done biology probably are familiar with this as well, because we use electrophoresis. In year 12 chemistry, we talk about how it can be used to separate proteins. But in year 12 biology, you'll talk about how it can be used to separate DNA fragments as well. And that also has a lot of scientific applications. Now, remember when we talked about amino acids, we talked about how they each have a different isoelectric point. So then, if we have a protein and we want to separate it into different amino acids, what we do is we have this gel. We put the protein in the gel, right? And the gel will have a very particular pH. Let's say it was like pH 7, just as an example. Um, and so then what happens is that we have a negative electrode, we have a positive electrode. So then amino acids, I'm just going to call them AA, with an isoelectric point that is less than 7 will be positively charged. So they'll go this way. And then amino acids with a pH greater than 7 will be negatively charged. So they'll be attracted to the positive electrodes and will go this way. Other thing to keep in mind is that because of those because of also the different sizes of those amino acids, they're going to travel towards the electrodes they are attracted to at different speeds. So then what this means is that if we stop this power supply at a certain point in time, we'll see each different amino acid at a different point, which then can help us separate all of them. All right. So that's all there is about gel electrophoresis, mainly used to separate proteins. Also used with this photo here, it's actually used like an application of it in DNA fragments. For those of you who don't do biology, you don't need to worry about it. For those of you who are doing biology, then it'll be covered in the biology unit 3 and 4 lectures, hopefully. All right. X-ray crystallography. This is one where it's listed in your syllabus. You just need to understand that it is a technique that is used to basically separate and analyze molecules and which molecules are present. However, you will not be asked to analyze data from X-ray crystallography, so I wouldn't worry too much about trying to understand data from it and things like that. I just want to understand how it works. So essentially what happens is that they crystallize a molecule and they hit it with an X-ray beam. And when it's crystallized, that means it becomes very reflective. It diffracts all of the rays. And then we have this film. We have the diffracted rays hitting different areas of the film. And then depending on how they hit the film, we can determine which atoms are present in the molecule. All right, that's all you need to know about X-ray crystallography. Now let's talk about infrared spectroscopy. So essentially, you don't need to know a whole lot about how they actually get this diagram here. But it's essentially just reading like wave numbers and wavelengths of a certain molecule as it goes through this device here. And it creates these little waves. Now, what we can do with this is that depending on where these waves are peaking, we can determine which functional groups are present in our molecule. So, for example, this little peak here before 2000, that's a representation of a C double bond O functional group. This little peak here represents an alkane. So then we know that there's a C double bond O in this molecule, and there's also alkane bonds in that molecule as well. Now, when you do these questions, anything below 1500, you don't need to worry about. It's for university level chemistry, not stuff you need to worry about. So first step in answering the question is just crossing it out. So that way you don't the function what we call the fingerprint region. You cross out the fingerprint region because you don't have to worry about it. Then like you might be worried right now because how are you going to remember what each of these peaks is actually for which functional group? Well, there's a big table on the data book, which I can actually go ahead and show you right now. Um, this table we can see here. Um, obviously, things in the fingerprint region, these things, I wouldn't worry about. But if we look at anything above 1500, see how it tells you the sort of range of each type of peak and which bond um, it actually symbolizes. So that's a C double bond C here, for example. So it indicates that what we have is an alkene or could be an unsaturated lipid. This is a C double bond O here. So could be a ketone, things like that. So you need to use your data book a lot for questions that involve infrared spectroscopy. But and that's another example here of like what these questions sort of look like. So here we have decane, it only has an alkane peak, so we only have this alkane peak here. Octane, she has a little peak here, which symbolizes a triple bond. We have the alkane peak here as well. And here is just an extra thing to sort of or an extra trick to sort of help you understand sometimes how the shape of the peak also tells you which functional group it is. So if it kind of looks like a tongue or like a really smooth curve, most likely it's an alcohol. If it's like a really sharp peak, then it's probably an amine. But then if it's a sharp peak and it's at the range of the alkyne, then it's probably an alkyne. But a carboxylic acid, like a carboxyl group doesn't actually have its own peak because essentially what you'll have is a C double bond O and an OH peak, but together they'll kind of look like this. But I'd probably try and watch out for each peak and sort of go from there. Here are some more examples of just triple bonds and how they show up, but this is not something I'd worry about too much. All right. Next analytical technique is mass spectrometry. And this is something you are probably familiar with in year 11. Yeah, in year 11, we talked about how we used it to determine the abundance of different isotopes. But in year 12, we have a different use for it. And also with mass spectrometry, most questions you'll get on it will involve mass spectrometry and IR spectroscopy. So here's an example of how we used it in year 11 where we have our isotopes. Also, like just a little bit before I go, like about how the machine works. It's like ionization and then it deflects all the molecules and detects them. That's like basically what happens, but you don't need to know too much about how the machine works. Main focus is how you can use the data to determine information. That's that should be your main focus in terms of the exam. All right. So, um, here's an example of how it could show up in terms of organic chemistry. So when all this ionization is happening, it actually what it does is it breaks like the bonds between carbons. So see how we have the hydrocarbon here? Like it might break the bond, say here between CH3 and CH2. Maybe here between the two CH2s could break the bond. Like say it could break the bond here, right? But or here. But it can't just break two different bonds like that and have a little functional group in the middle. That's really important to remember. So let's say it can break the bonds at like this point, at this point, at this point, or at this point. And it can only do it between two different carbons, and it can only do it at one point in the molecule. We can't just like yank this little functional group out of the middle. Um, that's not possible. So, and then what it does is that after it ionizes, um, like as this hydrocarbon is going through the machine and it's being ionized at all these different points, we get the abundance of all these little ionized molecules. So we might get so this 72 is the abundance of our total molecular mass. But if say ionized it here, we'll get like some of this showing up in our chart and some of this smaller mass here also showing up in our chart at separate points. So then when we have this, what this can sometimes help us is actually understand or figure out how many carbons we have in our organic molecule. All right. Now, next step is to jump into a question. But here is an example where we actually have a mass spectrum and an IR spectrum of our molecule. And why I said that most of the time we get both of them in our questions, we get both a mass spectrum and an IR spectrum, is because if we think about what each one is telling us, IR spectrum tells us which functional groups are present. The mass spectrum tells us how many carbons are present. So with both of these information together, we can actually determine the molecule. Now, what I'm going to talk about before I look at the working for this example is that first step when we're trying to actually determine like how many carbons there are from the mass spectrum, we look at the highest mass, which here is 60, right? That's our molar mass of whichever molecule this is. So if we say, for instance, if we knew for sure that our molecule was only hydrocarbons, right? So it only had carbon and hydrogen. What we do is that we divide by 13. So in this case, let's divide. It's not going to work in this case because just when we see the solution. But when we divide by 13, right? Or I'm going to try another example, right? Let's just say our peak was 39. Or let's say 38. We divide by 13, right? We get 2. I'm just going to do the little division here. Sorry, 38 divided by 13. So then we get 2 and remainder 12. Right? So then what then this means is that this 2 means that we have 2 carbons. So we have 2 carbons, and then we have the remainder plus the number of carbons, which is our hydrogens. Now obviously this is a random example, so it's not going to work in this case. But once I go through this example we've got here, you'll sort of see how it works. But another thing to mention is that when we don't actually know for sure that it's a hydrocarbon, then what we can do, say from the IR spectrum, we know that there's like an OH group. So we know that there's going to be 1 oxygen in there. So then what we do is we go 60, take 16, right? Let's do 60, take 16. So we get 44. And then we divide the 44 by the 13. All right. Now, and then we do the next steps to figure out how many carbons, how many hydrogens. Okay. Now, I'm not going to go too much in depth because I do have the full worked answer here. So, as I said here, let's look at what I did on just the diagram here. So first step was actually I found what the peaks mean. So we have an alkane peak, so that's the CH bond, and we have an OH peak. So we know that we have an oxygen in the molecule. So first step would be to take 16, which is the molar mass of oxygen, from our total molar mass. So that leaves us with 44. We divide 44 by 13, we get 3 carbons and remain the 5, so 5 hydrogens. So then we know that we have 3 carbons and then remain the 5 plus 3, sorry, which is 8 hydrogens. And we already know from just the mass spectrometry that we have the 1 oxygen. And since we know it's the OH bond, we know it's going to be some sort of alcohol. That's why I wrote it as C3H7OH. You can also write it as C3H8O if it makes it easier for you. Now, last step in questions like that is to actually think about how this mass spectrometer works and take that to actually figure out which isomer we've got. Because we already figured out that we have propanol. We have C3H8O, which is propanol. But we don't know whether it's propan-2-ol or propan-1-ol. How do we figure that out? Sometimes it can just be like, sometimes you will have to do trial and error multiple times, but sometimes it can work from the first time. So first thing I did is I drew propan-2-ol here, propan-1-ol here. I looked at one example of how this could ionize. So it could ionize here, leaving us with CH3. Could ionize here, leaving us with CH2OH. Now let's look at the CH2OH. C is 12, 13, 14. Sorry. 12, 13, 14, 15 plus 16 is 31. We look at 31, see how it is. We have 31 here. If you look at 15, if you look at, the propan-2-ol, we have here 12, 13, 14, 15. Let's look at 15. We don't really have 15 there. So that in itself is enough to tell us that the molecule is 1 propanol. Another thing we can do is we can just, try another bond just to see how it works. But like as we can see, this CH3 here, it can actually also be formed by this one. It's just a lot less common. But you can always, like if we draw another line here, right, and another line here, let's count the bonds here. So we have 12, 24, 25, 26, 27, 28, 29 plus 16 is 45. And then here, we have 1, 2, 3, 4, 5, and then 5 plus 24, 29. This is also 45. So that doesn't really help us. But I think the 31 versus 15 is enough because we can see how abundant 31 is, more than like the 15. And even actually our peak here, if you look at it, yeah, it's around 15, but it's barely there. Okay. So that's basically it for like analytical techniques. So I haven't included a quiz because we've already worked through that one question. And that's like the most common type of question to get on that topic. That's not to say though that you can't be asked about chromatography or electrophoresis. All right. With chemical synthesis, essentially what this topic is basically like we look at some really common industrial chemical reactions like that have like really common industrial applications. And then we look at like some conditions that we use to actually give them maximum yield. So a really common one, which you might be familiar with from your equilibrium topic, because it does show up in a lot of equilibrium questions, is the Haber process. Um, so the Haber process um, is basically where we use nitrogen and hydrogen gas to form ammonia. Now, this picture on the left side here basically shows you like how they do it in the factory. So obviously, because we have a lot of nitrogen in the air, we also have some hydrogen gas in the air. We don't see ammonia in the air all the time. And why is that? Because there are certain reaction conditions that we have to meet. Now, what are those reaction conditions? I think roughly it's about like 400 degrees Celsius. And I'm not exactly sure what the pressure is. But I think it's 1 to 2 atmospheres from memory. Um, but this information will also be on your textbook. Um, okay. So why 400 degrees and why 1 to 2 atmospheres? Why do we need high pressure and high temperature in this case? Um, well, first of all, first thing you might be wondering is according to equilibrium, we have this here plus heat. So as we increase the heat, we're actually driving the reaction backwards and we're decreasing our yield. But if we have the heat any lower than 400 degrees, then the reaction just won't happen fast enough. So despite the fact that lower temperature here would give us more yield, we still have to consider the rate of reaction. And the rate of reaction will be slowed down a lot if we decrease the temperature. Same with if we decrease the pressure. Because if we have, let's say, like a high pressure, right? Um, Actually, in this case, if we have a high pressure, it will drive the reaction this way because we have 4 molecules on this side, only 2 on this side. So it'll occupy the container a little bit less. So we use high pressure to actually maximize yield. We obviously don't want it too high because we don't want the container to pop. But um, with heat, we still have to consider, and even pressure, we still have to consider the rate of reaction. And sometimes, even if our equilibrium didn't favor high pressure, we still have to use a fairly high pressure to drive the rate of reaction. All right. Now, next common process in chemical synthesis is the contact process. Now, here is once again a diagram that shows you how it works. But what I'll talk through is just like how the chemical reactions are written out, um, because I think that just helps you understand it a little bit better. So before we look at the individual chemical reactions, the main purpose of the contact process is to synthesize sulfuric acid. So, and how we synthesize sulfuric acid, we start with solid sulfur. So, but it's not as simple as the Haber process because it's not just one simple chemical reaction that um, gives us the sulfuric acid. There's quite a few steps to it. So let's look at what those are. So, first step is we put sulfur solid and oxygen gas in a furnace like this um, to form SO2 or sulfur dioxide. Then the next step is an equilibrium reaction. So this here is where we have to give really careful consideration into temperature and pressure. Because like we need to have a high enough temperature so that the rate of reaction is fast, but also as we can see here, our like reaction still is exothermic and favors heat. So we also don't want it too high that it compromises our yield. Um, so our equilibrium reaction here is we mix sulfur dioxide then with some more oxygen. But to make this reaction to happen or happen fast enough, we need a catalyst, which in this case is vanadium oxide. So we use vanadium oxide as a catalyst that helps speed up the rate of reaction. Once again, so high temperature here doesn't actually favor yield, but we still need it to be in the 400 to 500 range for us to actually, not drive the equilibrium backwards. In terms of pressure, um, in this case, also we like our high pressure will actually also be favorable because we have three here, two molecules here, so that'll also drive the reaction forward. Um, but once again, not too high for safety purposes. Um, all right, and like the other thing with pressure is just as we said, is that it also increases the rate of reaction. All right, so once we have our sulfur trioxide, um, that's the step that actually when I was in high school I found very confusing. Um, so we actually, yes, we want to produce sulfuric acid, but we actually do need the sulfuric acid to produce more sulfuric acid. That's the point, like that's the thing with this reaction. Because if we look at the overall yield here, we have double the amount that we initially had, but we still need some sulfuric acid to start us off. So essentially, that third step is where we mix, where we put sulfur trioxide with sulfuric acid to form a molecule called oleum. And then oleum is hydrolyzed to form even more sulfuric acid. So essentially, we need to have sulfuric acid initially, but we just need to double it. And this is like how it works basically here. So we have like SO3 goes into this chamber, we put the concentrated sulfuric acid, and then oleum gives us even more sulfuric acid. All right. Now, next part of chemical synthesis is when we talk about biodiesel and ethanol production. So, if we talk about biodiesel, we have essentially we get like that's basically what the reaction is that we mix a triglyceride, which we're sort of familiar with triglycerides from our saponification reaction. Triglyceride is basically just vegetable or plant oil. Plant oil sometimes can be animal oil, but most of the time it's plant oil. Um, so these R1, R2, R3 chains are all like long hydrocarbon chains. So then we react it with methanol and a catalyst to form what we call fatty esters, or fatty acid methyl esters is the really long name for it. And essentially, these are the most common types of molecules in biodiesel. So that's essentially what the reaction is, and then we get glycerol as a byproduct. Now, just a little bit about how this works, just to sort of help you visualize this reaction. So let's follow the red line here. So we have that after this ester, we just have like a little CH2, CH, and CH2 groups. So essentially, what happens is that this bond is broken once we have the catalyst and the reaction conditions. And then we have from each glycerol molecule, we have an OH that actually bonds to each of those CH groups here. And that's what gives us our glycerol. Then that leaves, you know, oxygen here with an unbonded electron, or three oxygens with an unbonded electron. And now all these chains are separated. So then each of those CH3s from our methanol, because we need three methanols for the reaction. So each of the CH3s from our methanol are actually bond to this oxygen here, to this unbonded electron. And then we get three separate fatty acid chains. All right. Now that's all. That's what you mainly need to know about biodiesel. So let's talk about ethanol production. And like ethanol production is also really important. It's going to carry us a little bit into our green chemistry topic. And with chemical synthesis, like I get it can be a bit boring because it's just memorizing these reactions, but there's still quite a lot of questions on it in the external exam. So it's good to keep it in mind. All right. So hydration of ethene, pretty self-explanatory here. So essentially, we have um, we have our ethene. We add it with water, and we can see here how the carbon has a double bond. So this double bond breaks, right? And then one of the electrons in this carbon binds to this H here, and then the other electron just binds to the OH, and we get ethanol. But this doesn't happen spontaneously. We also need certain reaction conditions to meet this. So we need 300 degrees. And as we can see, this reaction is in equilibrium, and we also have heat as a byproduct. So I am going to emphasize again, um, like high temperatures here would compromise our yield, because this is an exothermic reaction. However, if we don't have a temperature high enough, the reaction won't happen fast enough. Let's remember we also need a phosphoric acid catalyst. Um, we also need a pressure of 60 atmospheres. And here pressure does drive the reaction forward and drives the rate of reaction upwards. Because as we can see, we have less molecules in the product side than the reactant side. All right. Now, let's talk about another method of ethanol production. So, and this is what we call fermentation of glucose. So the first step we do is that we have some sort of dye or polysaccharide. That's what our CH C12H22O11 is. So that's like in this example, it's a disaccharide, but we can get a polysaccharide. And this is essentially what we call a hydrolysis reaction. So with the name hydrolysis, like it's pretty self-explanatory when you think of the name. What we do is that remember how we talked about condensation and how with our glucose, like we have OH goes out, H goes out here, we get water, and then we have that little glycosidic bond. What then hydrolysis is that we add, we actually add water and we have certain reaction conditions and then it goes back to this form. So it's essentially just the reverse of condensation. So the first step so that we have enough glucose for this reaction is that we want to grab either a polysaccharide or a disaccharide and we want to hydrolyze it, um, so that we can break it down into individual glucose units. And there are special enzymes that can do that, which are also used in manufacturing for us to synthesize ethanol. So then it's quite a simple reaction. We have um, glucose here. And I'm just going to write a little note, sorry, that we have a yeast catalyst. And that's the main important condition that you need to remember about this. So then the yeast catalyst, what it will do is that it will break this glucose molecule into two ethanols and CO2 gas. All right. So we have our last little topic here, which is green chemistry. So um, green chemistry is basically what we use to actually assess how environmentally friendly um, certain chemical reactions we have are. So we have many things that we need to think about when we do this. So we think about how many greenhouse gases are produced. We think about how many, um, for example, like unwanted products or waste products that we produce which can't be used elsewhere. Um, and we also use atom economy to measure, um, how much product we're actually getting versus, how much reactants we're putting in. So um, here is the formula for atom economy. So we have an example reaction, A plus B equals C or C plus D. Essentially, we have our molar mass of our desired product over the percentage atom economy. So over the molar masses of each of the reactants, and we have that as a percentage. All right. So, for example, um, let's look at like what's it called? Ethanol synthesis as a example. So, let's go back to these slides and just look at the reactions a little bit. So, here we have hydration of ethene. That's our first method. So, we have ethene here, so C2H4 plus water, and then we get ethanol. And then we have here our other method where we get ethanol, but we also get CO2. So let's think about some parameters we have here. So first thing to think about is just before we even think about doing any working, let's actually just think about the green principles. So we look at, for example, hydration of ethene. We don't have any byproducts, but if we look at ethene, that's not like an organic source. So what that means is that it's not part of the carbon cycle. So if we use it, that's basically just going to increase emissions. Contrast that with glucose. You know, any polysaccharide, any disaccharide, um, those are all, you know, biological sources. So then what that means is that like they're already part of the carbon cycle. So even if they have emissions like we have here with the CO2, then that's still not really harming the environment because that carbon was already in the carbon cycle. Okay. And that is basically the first step when we solve this question because we discussed the green chemistry of it. Then we compare their atom economies. We talk about hydration of ethene, and we actually have an atom economy of 100%. So we don't have any wasted product. We look at glucose fermentation though. We actually have some byproduct. We have a lot of CO2 as byproduct, which actually only gives us an atom economy of 51.1%. But if we think about it, first of all, which one is greener? You might think hydration of ethene. Well, it's a higher atom economy and there's no byproduct. But at the same time, we have our glucose fermentation. The byproduct is actually useful in terms of like industrial wise because we use CO2 gas in a lot of things like fire extinguishers, like soft drinks, things like that. And the other thing is that it's not increasing emissions because it comes from an organic source. So it was already part of the carbon cycle. So then if we consider all these other aspects into account, we actually find that glucose fermentation is the greener choice of synthesizing ethanol, which is why it's the more common way of synthesizing ethanol. Synthesizing ethanol. All right, but that is all we have in terms of the lecture. Feel free to stick all your questions in the Q&A box, and I'll be here to answer them. So let's just go over some key skills just before we go, and just have some like basically just quick reminders about the main things we cover. So we talk about macromolecules. We have our we have our glucose, fructose, and glucose and fructose are our main monosaccharides. We have our alpha beta glucose, and we remember that how we have our polymers, which form our polysaccharides. So examples of those are like maltose, lactose, and sucrose. So these are dimers, and then we have some polymers like amylose and cellulose. We also have lipids, which are, used in terms of like soap, and they're also abundant in animal fats and plant fats. So things like vegetable oil, things like that are lipids. The main thing with lipids is that they are insoluble. And that's why, in terms of soap, we actually ionize a lipid or a fatty acid, and then we mix it with a metal ion, with a metal cation, to actually have what we call a fatty acid salt. And then that way we have a polar head, non-polar tail, and that actually, that both polarity and like being hydrophilic and hydrophobic actually helps dissolve the grease, which is very important in terms of the action of soap. Then we talk about proteins and how proteins are different. We have our primary, tertiary, and secondary structures, which are all formed because of our peptide bonds. And yeah, so we think about primary structures. They're straight chains. They're they're basically because of peptide bonds which link the amino acid monomers. Think of secondary structures. We think of like the bonds between the C double bond O group and the NH group. Tertiary bonds are bonds between side chains. And that's what makes proteins so different in terms of their structure and their properties, because they're all folded in different ways and they bond with each, like the monomers bond with each other in many different ways, which actually gives proteins their versatility. And that was all we talked about in terms of macromolecules. When we talk about analytical techniques, remember, we talked about gel electrophoresis and how it uses the different isoelectric points of amino acids, and how they have different charges at different pHs, and it uses that to separate them. And it has other applications as well, but that's the main one we need to talk about in chem. We also talked about, remember, infrared spectrometry and infrared spectroscopy and mass spectrometry, to determine the type of high organic molecule we have. We also talked about chemical synthesis. So remember the Haber process, synthesis of ammonia, contact process, sulfuric acid synthesis. Biodiesel production is through triglyceride and methanol, and then ethanol production is through hydration of ethene and glucose fermentation. And then we also talked about green chemistry and some principles with that. So main reminders is that you memorize all these processes and the reaction conditions, because they're not on your formula sheet. You are expected to know them. Having a really good understanding of your analytical techniques and considering green chemistry in some industrial reactions and applications, and also macromolecules. Most things in regards to them and their structures aren't given on the formula sheet, so it's really important that you understand them and their structure. But anyways, that was all from me today. And good luck with the rest of the term. Thank you.